do is you can make this substitution right into here. Alright, and this is what simplifies things. Or you can go mv squared. Actually, you go mv squared over here. You can go. So this equals. So you have you put a half in front of this and a half in front of this. So a half mv squared is ke squared over r. So this equals a half ke squared over r minus k e squared over r. Alright, and that comes out to be equal to minus a half k e squared over r. Alright, so that turned out to simplify. That's one of the tricks that, you know, really helps your algebra to simplify some things. Alright, and then Rn, you know, I just did by substitution. Alright, I'm still going to let you guys struggle on it, but that was one of the tricks, alright? If you saw that, that was one of the algebraic tricks that helps out. Alright, or it helped me out, yeah?
What I did, I put the value for r in that equation.
Right.
And r equals to n squared a naught.
Yeah.
And you just put it in there and then solve for en.
And then you get en, that's right. So then the only thing I'm not showing you really is that you can set up the equation to solve Rn. And so for Rn, here's what you do for Rn is, okay, so for Rn,
I use angular orbital dimensional equations.
right, that's when you've got to use L equals Rnb, which equals n h bar, right? And you can solve for R, right, equals n h bar over mb. Alright, and then
I start off my base guy, the Coulomb force equals the centrifugal force, not really Coulomb force.
right here, yeah.
Right.
And you substitute it right in.
Yeah.
Alright, so that was kind of trivial. The harder part was the energy. It got to be very messy unless you saw that substitution. Alright, so how many people got Rn? How many people got En? Alright, so Elmar, you got it? Alright. Okay, and then when you plugged in the numbers, how many people got the right numbers for the Bohr radius of a half an angstrom? And then the energy is minus 13.6 eV. Okay, so if you didn't get it, make sure you can get it. Alright, maybe try these tricks, but keep at it because this is one of the things you have to be able to do, I think. I mean, this is a very easy way to solve for a hydrogen atom, and the story goes a long way. Okay, so let me continue then with that. So then I'm going to start. We had the picture of, we had the story where we had the two forms that we talked about the article, and in the article you had the Heisenberg formulation, which is matrix mechanics, and then we had the Schrodinger version, the wave equation, all right, and that was around 1926. And the nice stories between those, and then Schrodinger was able to show that the wave equation is essentially a different representation of the matrix equation. All right, and the way he was able to show it is a little about some math that I'm going to talk about because we do when we do Fourier analysis. But the big idea is that the solutions to Schrodinger's equation that we're going to use are square integrable. And what I mean by, ultimately what I mean by square integrable means that they can be used as a probability and add up to 1. But square integrable functions form a Hilbert space of functions, and a Hilbert space of functions has all the properties of vector spaces. So in other words, the solutions, wave function solutions, have all the properties of vectors, and therefore you can represent them as vectors and matrices. Okay? But what we're going to do is we're going to do the wave formalism, and in the wave formalism, alright, Schrodinger was inspired by Peter Debye, his comments, where's the wave equation? All right, and the reason that Peter Debye asked where's the wave equation, because Schrodinger was bragging about the de Broglie wavelength, the lambda equals h over p. All right, so they were having a conference and a seminar, and Schrodinger was talking how great this wavelength is, and then Peter Debye said, "Where's the wave equation?" Right? Okay, so here's now Schrodinger's thinking, and again, here's 1900 light equals a wave, an electron equals a particle. Okay, after 1900, light, through those various experiments, was kind of wave plus particle. And so we're now solved with the electron about hydrogen. All right, so it's definitely a particle, but Schrodinger's idea is to look at it and say, well, the evidence was showing, and the de Broglie wavelength was saying it's showing that it's also wave-like, right? So that the electron is particle in a wave. So what Schrodinger did is he said, well, where is the wave equation for light? That's Maxwell's equation. Right? And so essentially what Schrodinger did to find the wave equation for the electron, he started with Max's equation. So everybody got it? The motivation? All right? So that's what we're going to do. So let's start with light. Double slit experiment. All right? And so here's the scoop. If you start off with laser light, and the only thing that I mean by laser light is that it's coherent and a bunch of other things, but it's a particular wavelength. All right, well, the light from here has a whole bunch of different wavelengths and a whole bunch of different frequencies, and it's not coherent. All right, coherent is important, but I guess I'm not going to talk about it right away. All right, and if you send a laser light through this device right here, I'm just going to put it right here. It's called an attenuator. It's just a device that can limit how much light goes through. Okay, so I'm going to be able to control it. I'm wide open, all the light goes through, and when I close it, less light's going to go through. All right, and then I'm going to impinge this light on a double slit, and then I'm just going to have over here a detector. Okay, so let's say that this is x equals 0. So this is going to be, I'll call this plus x direction. This is minus x direction. And so if you want to think about a coordinate system, if I have x this way, right, I need to make sure that I have a right-hand coordinate system. So what should this be? X cross y equals z. So this has to be z and this has to be y. Right? So that y cross z, put your thumb in the direction of x, the right hand. Is that right? Okay. So that's what the coordinate system looks like. All right. So if this is light, then something happens. When I come over here, believe it or not, you guys know this, you're going to end up with what's called a double slit interference. And you end up with this. You end up with light over there. Now, what is this? The detector detects intensity. All right? And intensity is the thing that we really measure and what we really kind of feel, and I'll explain why. Intensity is actually energy. So energy per unit area per unit time. In other words, it's power per unit area. So watts per meter squared. All right, that's what you feel. So the big example I do with this is the following. intensity is what you feel. For example, if I took a match, right? A match, a flame, and I put it on your arm right here, you would feel it, right? All right, but what if I took that flame, that match, and instead of the same energy that's in that match, and instead I distributed it about your whole body, so you wouldn't feel it as much, right? Or what if I took the energy from that match and I distributed it not instantly, but I gave it to you over, say, an hour, over the course of an hour, you wouldn't feel it. Now, in both cases, the same amount of energy has been deposited on you, but one was deposited over a bigger area, and one was deposited over a bigger time. But the same amount of area the same amount of energy was given. So what you actually feel is intensity, right? It's the power per unit area. Okay, and that's what this measures. All right, so in other words, it's more intense here, but it actually goes to 0 in the middle. Sorry, guys, it goes to the middle. It goes to 0. Okay, so we have to figure out how you get this intensity pattern, how you get this interference pattern. So because it's light, what you want to do is you want to look at Maxwell's equations. All right, so here's where the light is. The light's in here, and something's happening to the light so that it's going through, these slits and causing this interference pattern. All right, so in here are Maxwell's equations. The divergence of E equals rho free over epsilon naught. The curl of E equals minus dB dt. The divergence of B equals 0. And the curl of B equals mu0 J free plus mu0 epsilon naught on dE dt.
So those equations hold true for the light in that area, but not outside that area?
They hold. These are the equations of light. Period. So they govern light everywhere. Everywhere.
But there used to be Ampere's law and Gauss's law and different things.
So these have names. This is isn't this called Gauss's law?
That's Gauss's law.
And I think this is Ampere's law, right? So these have names. And this is Faraday's law of induction. All right, they have names. I mean, I could talk forever about Maxwell's equations, but I'm not going to do it. All right. The Maxwell's equations are awesome. You guys should all have seen Maxwell's equations now and have a feel for them. I'll do this real quick. What does this equation mean? I don't care about its name. I don't care about. You got to tell me, what does it mean?
Electric fields diverge.
So what does that mean?
They go from a point. They go out and all.
Okay, so what this means is point charges are the source of electric fields that go divergently outwards. That's how you read Maxwell's equations. So the first one means charges source electric fields that go out. This is how I look at it, guys. And again, I'm not going to kill this because this is. But I look over here, and this is important, so you'll never forget it. All right. These things are the sources for these fields. So rho is the charge density, how many charges you have per unit volume. So charges source electric fields that diverge. Right? Okay. Now, curling E fields are electric fields that go around. Right? So read it that way. Here are electric fields that go out. Here are electric fields that go around. What are the sources for electric fields that curl?
Magnetic fields.
Time-changing magnetic.
Changing magnetic fields. Time-changing magnetic fields cause curling electric fields. All right? What are the sources for magnetic fields that go out? There is none. There's no such things as magnetic. There's no little point-like sources of magnetic fields that shoot out radially. There are no magnetic monopoles. There are no magnetic monopoles around us now. Right? Yeah.
I was picking up like some copper wire to do the electric motor experiment this summer. Class is teaching.
Yeah.
And the guy at Home Depot was like,